Hi, and welcome to another edition of Ordinary Differential Equations. Today we are going to start a new chapter on second order equations and the method of solving the simplest case of them. Let's go take a look at the problem that we are facing now. So, general second order linear equation has the following format. Some function of x times y double prime plus some function of x times y prime plus some function of x times y is equal to another function. This is the general linear case. Typically, these type of problems are not easy to solve, so that we are going to go ahead and specialize on what we can do at this stage. These type of problems always come with some initial condition. The value of the function at some point, value of the derivative of the function at the same point are given. And under appropriate conditions that are very similar to what we saw with the first order equation, we have existence and uniqueness, meaning if you go ahead and standardize this equation by dividing with the leading coefficient, so the leading coefficient becomes 1, then the domain of existence and uniqueness is going to be a region where the three functions that you have here will have continuous presence and contain your initial condition. To the extent that you can guarantee all those conditions, you will have existence and uniqueness. But we are not going to focus on that type of a theoretical issue. Rather, we are going to go after problems that we can actually solve easily and have direct contact with the simplest application. Remember in the previous lecture that we said the vibration problem can be modeled with this following differential equation. I forgot to put my prime here. So we had my double prime plus cy prime plus ky equal to 0. M was representing the mass, c was drag, and k was spring. These were positive numbers. And then y of t0 meant the initial position, and y prime of t0 meant the initial velocity. That is our long-term goal, to understand how the vibration goes. However, we are going to go ahead into a mathematical setting where we have some generic function y, and its the first derivative and second derivative entered in this equation. A, B, C for us are any constant, so long as our first coefficient is not 0. This is considered fair game for us. So they could be negative, positive, or in fact even complex numbers. They would be okay for us. In the physical applications, they are all positive. So we are going to go ahead, take a look at this problem and see how we are going to solve it. Before starting that, let's become familiar with the terminology. If these are variable coefficients, that's where the difficulty will be. That is something we are going to study perhaps later on. Right now, A, B, C are going to be just some constants, so there's going to be no variable in these locations. Next item, this terminology homogeneous refers to the right-hand side being 0. So when the right-hand side is 0, the equation is called homogeneous. We are going to explain later on what that means. It essentially means the forces in the problem are limited to what we have mentioned here. If you have an external variable force, that typically is a more complicated problem. We are going to look at that at a later stage. So let's see how do we approach solving this. Instead of that method of integration, integrating factor or separation and such, we actually go ahead and solve this for all the cases. We in fact have a simple recipe for solving them. To motivate that, let me start you off by something from a first order case, and then we'll see how second order case can be solved in a rather similar style. So let's go back to a first order example from the beginning of the course. Suppose I have a problem such as 2y prime plus 3y equal to 0. This is of course very simple, and by now you know immediately what the solution is. But suppose we just remember that its solution was some sort of an exponential. We just don't remember the details. So we start with that guess. We say suppose the solution is some exponential with some constant multiple, and then I write exponential of, and I don't know what number goes in the exponent. Let's for the moment call that number r x. Well, y prime, the derivative of this c being a constant, will be simply c r e r x. If I take these two and plug it back into my equation, given that this is supposed to be the solution, 2y prime will be 2c(r)(e)(r)(x), and 3y will be 3c(e)(r)(x). Well, I can factor c(e)(r)(x) from this, and I will be left with 2r plus 3. And since the equation is supposed to be satisfied, this has to be 0. Well, how can this thing be 0? Let's investigate all possibilities. One possibility is to set c equal to 0. Well, then your y will be 0, and then your equation turns out to 0 plus 0 is equal to 0, which is not all that exciting. So if we set that aside, we say that saying c is equal to 0 will be giving us a so-called trivial solution, nothing so interesting. So we leave that out and intentionally say that perhaps should not be 0. Exponential of rx, that is never 0. Exponential perhaps at infinity becomes 0, but at the intermediate value of x, this does not become 0. The only interesting thing that we can go after is that 2r plus 3 has to be 0. Notice how this equation just resembles that one. Instead of y and y prime, we have 1 and r. Otherwise, the constants are exactly the same. Well, this is a easy equation to solve. R becomes 3 minus 3 halves. So I have figured out what r is, and the solution is some constant multiple of minus 3 half x. So in this case, we have a guess as to what the solution looks like, and then we adjust some component of our guess to see if actually our guess is correct, and we can actually solve the equation by that style. Right now, the way we are going to solve this equation or that equation is going to be of this style. We are going to have a guess that our solution is exponential. We plug it back there and see if it works. If it does work, then we do get our solution, and then we can appeal to our theorem on existence and uniqueness and say, well, this is the solution. So suppose I have an equation that reads like a y double prime plus b y prime plus c y equal to 0. We keep insisting that a should not be 0 because otherwise this becomes a first order equation. And then a, b, c can be any constant numbers. A, b, c are constants. This is important that they don't have any of the independent variable, either t or x, in them. They're just numbers. We start with the same guess that our solution is some constant times exponential of some multiple of x or multiple of t. Just as before, we notice that this constant is going to just filter all the way through and not going to play any role. So we just keep having it around without expecting anything out of it. We differentiate again. We take these ingredients and plug it back into our equation. So it's going to be AKR squared exponential of Rx plus BKR exponential of Rx plus CK exponential of Rx. All of these things have to be producing that zero for us. Just like in the first order case, I can go ahead and factor exponential of Rx out of this, and I'm left with AR squared plus BR plus C equal to 0. With the same discussion as before, this better not be set to equal to 0 because that gives us a trivial solution. This is just not 0 anyway. The entire burden falls on the shoulder of this expression. That is, the expression has to be equal to 0. So AR squared plus BR plus C is equal to 0. Again, we notice that how closely this resembles the equation that we are looking at. This equation is important enough to have its own name. It's called characteristic equation. And the roots of it are called characteristic roots. That is, you have an equation, you go ahead and solve it. It's a quadratic equation, so you have two roots. And you call these things characteristic roots. Somehow they characterize our equation for us. Let's go ahead and pick a specific example so that it just doesn't look too general. Suppose I have an equation that reads, say, y double prime plus 5y prime plus 6y equal to 0. So if we go ahead and try to find what exponent will work in this solution. So that leads us immediately to the characteristic equation. Well, this is a friendly quadratic. You have solved many of these things in high school. You immediately go ahead and factor it, set it equal to 0, and you get the solutions. Here's the first surprise. We were looking for one R that works. Here we got a bargain. We got two of them instead of just one. So what does the first one mean? So first one, it tells you exponential of minus 2x is a solution. And if you multiply it by any constant, still a solution. Second one says, well, exponential of minus 3x is a solution. And in fact, if you multiply it by any constant, that is still a solution. Let's call this constant, say, L. What we are saying is that that's a function that satisfies our differential equation. Let's just go ahead and verify exactly how this thing is going to happen. So suppose I am asked to verify that any multiple of exponential of minus 2x is a solution of this equation. How do I go about verifying? Well, differentiate, plug it back here, see if it indeed becomes 0. Excuse me. So the derivative is minus 2k. And the second derivative, minus 2 times minus 2, that becomes 4k exponential of minus 2x. So if I combine them by taking 1 of this and 5 of this and 6 of that, that is 1y double prime plus 5y prime plus 6y. 1 of this will be 1 times 4k exponential of minus 2x. Excuse me. 5 times minus 2k exponential of minus 2x. And then 6 times the original. 6 times of just. So what do I get? Let's factor exponential of minus 2x times k out, which is common to all of these. So from the first one I have 4, second one I have minus 10, and last one I have 6. And of course 4 minus 10 plus 6 is 0, and times anything that will be 0, that's how I'm rescued. So we see that an exponential does come to rescue, and the solution of our equation becomes that. Well, how about the other one? Well, the other one is also a solution. I leave it to you to go ahead and verify. So let me ask you to go ahead and verify that exponential of minus 3x is indeed a solution. So go through the same exercise, take a derivative, plug it back, clean it up, and see that the magic actually happens and we actually have a solution. Another very interesting fact appears here, and that is in engineering referred to as a superposition principle, and in mathematics you see it oftentimes under the title of linearity. It says that if I have these two solutions and my original equation has certain nice features to it, if this equation is linear and homogeneous, then the sum of these two solutions is also a solution. That is, if I take k exponential of minus 2x, into that I add L exponential of minus 3x, then that is the solution. Now, what we are going to state is that this combination covers all possible solutions of this differential equation. There is nothing that's left out. This is the unique solution of that, subject to determination of k and L. Well, how do the k and L come about? They are typically specified through your initial conditions. That's the simplest way. So let's go ahead and try another one. Suppose I ask you solve y double prime plus 7y prime plus 12y is equal to 0, subject to constraint that at time 0 this function is 1 and its derivative is 2. So this is a basic second order ODE with an initial condition, and we want to solve it. So let me again ask you that you go ahead of me and solve this, and probably it should take like a minute or two to put all the ingredients together. Okay, so you pause and do this. So step one is to write the characteristic equation. This coefficient is 1, so it's just r squared plus 7r plus 12 is equal to 0. It must be our lucky day that all of our quadratic equations are so friendly. So I get my r to be minus 3 and minus 4. So that tells me that my solution is k exponential of minus 3x plus L exponential of minus 4x. The question is, how about k and L? Well, the function and its derivative are subject to some constraints here. So let me write the derivative as well. Y prime is minus 3k exponential of minus 3x. This is minus 4L exponential of minus 4x. Then what? This is at x. Our initial conditions are at 0 typically, so we replace x by our initial value of x and enforce these two conditions. So y of 0 will be, it's very easy when you replace by 0, these things just become 1. So I have k plus L equal to 1. And then y prime 0, I have minus 3k minus 4L, that's supposed to be the other one. So these two equations together form a so-called system of linear equations. Now, if you have taken your linear algebra before this, you have seen a much more extensive version of this, but definitely you have done this in high school. This is a 2x2 system, so you have a variety of ways of solving it. Any of them is good, substitution or elimination or Kramer rule or whatever. Plenty of them are out there. Later on, we might have bigger systems, and perhaps we are going to talk about some help in solving them, but 2x2 should not pose a challenge to us. So let's go ahead and try one of these typical methods that you come across in high school. Say I want to do this equation, so I go ahead and multiply this equation by 3, add them up. That's going to be method of elimination, because when you add them, 3k and 3k cancel each other out. You have 3l minus 4l, so that becomes minus l, and you have 3 and 2 is a 5. So your l is minus 5. Now, to get k, you have two options. One is to plug this thing back here and get your k, and the other one is to go ahead and eliminate l. Either way is fine. So let's suppose I substitute, and then I get my k is equal to 6. Given that we have a lot of things invested on these numbers, it's best policy to go ahead and do a double check on this thing to make sure it's correct. So how do we check it? Of course, this came out of the first equation, so putting it back there is not going to be much of a check. We put it in the second equation. Second equation says minus 3 times 6. That's right, minus 3 times 6. And then minus 4 times minus 5. Now, since we're checking, is this thing 2? Well, of course, minus 18 plus 20 is 2. So we are more confident on our answer now because we checked. So what's the final answer? The final answer now, I have y is equal to k, which was 6, and l, which is 5 minus 5, exponential of minus 4x. So that's the solution. Now, any solution who has been looking at this notices some falling rocks ahead. Falling rocks ahead. So what is it that is falling? So we are looking at this equation to solve, and it leads to this so-called characteristic equation. I'm definitely sure that you remember from high school a little bit of issue when you're solving an equation. Aside from being lucky here that we got our answers so nice and clean and so on, there are in fact 3 possibilities for your characteristic roots when you're solving an equation. This is very crucial observation, so I want you to go back and write down for yourself what was the story of quadratic equation, general formula, and the 3 cases of the quadratic equation. What do you expect to happen? So here's my quadratic equation. Let's go ahead and, so quick review of quadratic equation. So we have AR squared plus BR plus C equal to 0. The solution of this, one of the main achievements of humanity going back to perhaps 3,000 years, is this formula. And it would be good for you to ask yourself, where does the formula come from? But what is the formula? What is R equal to? So quickly go through that in your head. Make sure you get this thing right. So minus b plus or minus b squared minus 4ac divided by 2a. So it would be nice if some of you actually show a curiosity as to where the formula comes from. But right now, let's move on. So the falling rocks, or the obstacle we face in solving this, is what's going to happen with the radicand, the value of the expression inside the radical. Well, if this is positive, we have a typical situation that we have two roots, and those two roots are real numbers, yet they could have radicals in them, but they're just ordinary numbers. Very interesting case is, what if this is a negative quantity? If this is a negative quantity, our roots are going to become complex numbers. And why is that an issue? Because this root shows up in the exponent, and we have to make sense of what does it mean to have an exponential of a complex number. So that's going to be a huge issue for us. Sometimes back in elementary classes in high school, they say, well, this doesn't exist, let's put it aside, it's not real. Some sort of adjectives are used that kind of bias the situation against these solutions. But now we don't have that luxury anymore of saying that let's put these things aside. We are going to see very shortly that, in fact, that's the most interesting case. Remember, we are talking about the vibration problem. And, in fact, vibration is associated with that square root of a negative number we are going to see. So this, we no longer can say, well, let's just throw that case away. It's not significant and such. So first of all, we make a letter to indicate what is inside the radical. Typically, that is shown by a delta and has a name for itself. It's called discriminant. Discriminant because it discriminates between three cases. It separates three cases. One is your discriminant is a positive number. So that's the one that's not going to give us any headaches, just some numbers. The one that is most interesting, more interesting than this, is when the discriminant is negative. So in the first one, we had two real and distinct, because one is obtained by addition, another one is obtained by subtraction, two real distinct roots. You might call them R1 and R2. And once you have those roots, your solution is easy. It's just k exponential of R1x and say L exponential of R2x, just like the problems we did. If delta is equal to a negative number, we are going to have two complex roots. One is obtained by adding, one is obtained by subtracting. And if you remember from your college algebra or pre-calculus, the name of a pair that comes like this is called the complex conjugate roots. So we call this two complex conjugate. Two complex conjugate roots, you can still call them R1 and R2, and you can put it up there in the exponent, and that is actually perfectly all right and correct. There's nothing wrong with them. The only thing about them is that we have no feeling for what they are. What does it mean to have exponential of some complex number times x times time or whatever. The issue is our understanding of what we are writing. Other than that, mathematically speaking, everything is correct. Well, later on in some of your further engineering classes, most notably in circuit analysis, they're essentially going to tell you, like, just get used to complex numbers. Just about everything is a complex number. So we are not going to kind of try to sugarcoat it, reform it or something. Well, it's complex. That's tough luck. Let's deal with it. But we are not there yet. We are going to insist on writing our solutions in real appearance, meaning all the entries of our formulas are going to be real entities. So suppose these complex conjugate roots, one is obtained by addition, another one is by subtraction. We write it as, say, alpha plus or minus I omega. So a complex number has two components to it. It's called the real component and the imaginary component, and that's how they look like. We are going to explain that if you have a complex conjugate in this format, then the solution can be written like this. Y is exponential of alpha x times, say, a cosine of omega x and the b sine of omega x. So if we have complex numbers, then trig functions are going to creep into our solutions. And that's exactly where the origin of vibration is going to be. Vibrations are associated with trig functions. And trig functions are born when the solution here is complex number. And that's how it's going to go. I'm going to explain how does this modifies its form and becomes that. For that we need the very famous Euler formula. But right now we're just stating what the overall look of our solution is going to be. The third case is the intermediate between these two. What if our discriminant became exactly zero? What if we are at the boundary between the real and complex case? So if this becomes zero, adding and subtracting would not make it then. It would be same answer. That is, in this case, R, both R1 and R2, both of them minus B over 2A. The case sometimes is referred to as having twin roots. So this is both R1 and R2 are same numbers. Many different terminologies are used to refer to having two roots that are identical to each other. So the words that are used, sometimes these are called twin roots, sometimes they're called double roots, sometimes are referred to as identical roots. All sorts of terminology is used to indicate something special happened. Some of the terminology is related to playing dice, some of them playing cards, and so on. It's like you have a pair, so you can say you have a pair, two of a kind or something. The official name in mathematics is a root of multiplicity 2. Root of multiplicity 2. You have two roots that are the same. So if we had 10 roots that were identical to each other, we would have called that a root of multiplicity 10. What would happen in that case? What would the formula related to this? In that case, your formula becomes y is exponential of either of these two numbers, the same number, so it's rx times, say, ax plus b. So we have three possibilities. Ordinary situation, when delta is positive, you have two distinct real roots, and then the two examples that we have done are examples of this situation. Then we have a situation where the discriminant will be negative, and our solution is a product of exponentials and trig. And a third case, rather rare and in-between case, is where our solution becomes exponential times a polynomial. If you remember in the previous lecture, we said we are going to see the so-called pet functions over and over in this course, because they are very versatile and they are enough to show a certain number of features for us. So pet function P stands for polynomial. Polynomials are this type of creatures. These are polynomials. E stands for exponentials. Exponentials all over the place. And T is for trigonometric, just the sine and cosine. The other trig functions are not going to be our friends. We are just sticking with sine and cosine. So there is a nice little theorem that says if you have a homogeneous differential equation of any order, doesn't have to be second order, it could be of any order, your solutions are mix of these kind of functions, exponential, trig, and polynomials. Now let's go ahead, take a look at two other cases just to see how it is going to be working out. So here are some examples for case of my word, was acting up. Okay. Suppose I ask you to solve y double prime plus, say, 6y prime and, say, 13y equal to 0. Okay, maybe we solve this with multiple pauses. Pause number 1, go ahead and get me my characteristic roots. Get me my r's. Okay, so if this nice scenery motivates you, so perhaps you're going to finish this course and you're going to end up with your engineering degree and you get rich and you buy land that is just has a stream right in the middle of it. Maybe that's going to be a motivation for going ahead and solving this problem. Let's see. So what happens? Well, step 1 is easy. R squared plus 6R plus 13 is equal to 0. You can use the formula, you can use the completion of squares, if you remember that from high school. So R is minus 6 plus or minus 6 squared minus 4 times 1 and 13 over twice leading number, minus 6 plus or minus 36 minus, what is that, 52. So R becomes minus 6 plus or minus square root of minus 16 over 2. So that's where the headache is. How do we handle square root of minus 16? Easy. So square root of 16 times square root of minus 1. This is whatever it is 4. Square root of minus 1 to avoid all sorts of mistakes and to avoid writing so much. Here's a notation for it. We call it I. In engineering, they call it J because I is reserved for electrical current. So by next year, perhaps you're going to get used to a 4J here. But either way, so then we come and say minus 6 plus or minus 4I over 2. Common mistake students make is to just divide this thing by 2, write minus 3 plus or minus 4I. So of course that is not a good form. You have to factor and then divide. So minus 3 plus or minus 2i over 2. Now you can cancel. You have minus 3 plus or minus 2i. Okay, now what? We have a real part is just minus 3. We have imaginary part which is just 2. Our solution, we have not justified why this is a solution. How does that one turn into this? But let's move on. Exponential of minus 3x times some multiple of, or no, any letter you want, it's fine, a cosine of, this is our frequency, 2x plus b sine of 2x. So when we have complex roots, notice neither plus or minus, neither nor I are going to be brought in with us. So a mystery question, but probably most students ask is, where did the I go? We are going to come to that later on. So let me write one of these equations and ask you to solve it in a matter of a minute. So suppose I have y double prime plus 10y prime plus, let's write 29y is equal to 0. So go ahead and solve this thing for me and make sure it takes less than 2 minutes. So of course we have r squared plus 10r plus 29 equal to 0. Let me solve this by completion of square, something that we need later on. So you can write this thing as r plus 5 squared, and you need to borrow 25 from this, and a 4 is left on. So r plus 5 squared becomes minus 4. So r plus 5 becomes plus or minus square root of minus 4, which we are advised to write as 2i. So r becomes minus 5 plus or minus 2i. Therefore, our solution becomes exponential of minus 5x times some multiple of cosine of 2x and some multiple of sine of 2x. Okay, did this agree with the solution you obtained? Now, of course, if you had the initial condition, then you go ahead and apply that. It's going to be a little bit more extensive than the previous problem we did, but still doable. So that's case 2. We said that is the most interesting case we are going to deal with because that ties in to vibration. To be complete, we have to deal with the intermediate case 2. Well, this is rather rare that exactly becomes 0, but we have to take that into account as well. And mathematically, those type of cases, borderline cases and such, become most confusing of all cases. Even though physically they do not mean much, mathematically they do, and to tie everything together, we have to pay attention to that case as well. So let's go ahead and see how is that case handled. Suppose I have an equation such as y double prime plus 6y prime plus 9y equal to 0. So of course that has a characteristic equation 6r plus 9 equal to 0. You notice that if you want to do this by completion of square, it becomes r plus 3 squared. There is no number left over. There is no additional number. That's why when you write this thing as ordinary type of a factorization, you have two identical factors. So the root of this thing is minus 3 and the root of this one is also minus 3. Sometimes some students and even some books go ahead and say you have one root. But it all depends by what you mean by that you have one root. Just in case you have kids and they are twins, you don't say I have one kid because they look like each other. Here also you don't say I have one root simply because the two roots are identical to each other. There is a word of difference between one kid and two kids that are just identical to each other. Same way in mathematics. In fact, it causes also the confusion. So if you wanted to apply the quadratic formula, what would have happened? You would have said minus 6 plus or minus 6 squared minus 4 times 1 times 9 divided by 2. Well, here's the issue. This becomes 36 minus 36. And so that's minus 6 plus or minus 0 over 2. Well, it doesn't matter if you add or subtract. In either case, you get minus 3. So again, you remember we saw a variety of names are used to indicate the situation. Twin roots, identical roots, pairs, two of a kind, or root of multiplicity 2. And what happens in this case is that the solution becomes exponential of minus 3x times some polynomial of order 1, just ax plus b. Where does this come from? There are several ways of justifying it, all of them mathematically involved one way or another. But right now let's go ahead and practice and become familiar with the fact that there are these three possibilities ahead of us, and we have to be comfortable switching back and forth between them. Now, many textbooks treat these three cases separate from each other, starting with what we started with, cases like this. And somehow that students learn that very well, and the other two does not make enough of an impression on them, and they make certain type of mistakes. So I presented all three cases at the same time without going into too much detail about them, just so that you see there are three possibilities. So let's recap. We have a characteristic equation. It has two roots. There are three fates that this pair of roots can have. So there are three cases here for us to pay attention to, all depending on what's inside this radical. If it's positive, we have two distinct roots, and that's the ordinary situation with exponential of one of these things times x and exponential of the other one times x. The most interesting case is where this radicand is negative. When you are going to get two complex roots, and the solution is going to be exponential of the real part times sine and cosine of the imaginary part times x. Just that number, not the I. And that in between case is when that entity is 0, you get two identical roots, and we have a solution that has this format. Notice presence of pet functions, exponentials, tricks, and polynomials, and let's become friends with them because we are going to see them over and over again. Okay, I explained all three cases. Next lecture, we are going to look at them in more detail. Until then, good luck and God bless.